Hi guys, welcome back to Data Every Day. Uh, Today we're looking at a data set of used car catalog, a used car catalog, which is basically just a bunch of different used cars and a lot of very nice features for each one. And we're going to try to be predicting the engine type, which I believe has three values: gasoline, diesel, and electric, based on the other features. Alright, so let's get into the notebook. And I may have given a spoiler at the top. 100% accuracy is what we will be achieving today. Um, it's because the dataset is so nice and it has all these really nice features and very few missing values. We will be able to achieve 100% very easily. Alright, so let's get into it. We're importing NumPy and pandas for just working with the data. We're going to use matplotlib .pyplot and Seaborn to visualize the correlations between the features, and then we'll use the standard scalar and train test split function just to pre-process it a little further. We will use TensorFlow to create our model. So I'll go ahead and import those, and then I'll load in the data using pandas.readcsv. And I can get the file path right over here, cars.csv. I'll just paste it in, and we'll take a look. And you can see we have 30 columns, which exceeds pandas limit for what it will show in the notebook. You can see this ... means there's columns we're not seeing. So I'm going into the console and I'm typing pandas.setOption, and the option we're setting is max columns. I'm going to set it to none. Now if we reload this again, you can see we can see all the columns and we're good to go. Alright, so first thing to do, let's take a little peek into how many missing values we have. And from a glance, I don't really see any. Just to make sure, let's print out total missing values. And we can get the total missing values by accessing the data.isNA data frame. So data.isNA will just look like this. It'll be the data frame, but it'll be true-false values, and we'll only have a true if there's a missing value there. If we sum across the rows, so from top to bottom, we'll get the number of missing values in each column. If we then sum again across the columns, we will get the number of missing values altogether. And we have 10 missing values. So let's make a new markdown block here called filling missing values. And let's get a list of all the different columns that have missing values. Now there's probably not too many of them since there are only 10. Print columns with missing values. And I can get this by taking this data.isNA data frame again, and we're only going to sum once, this time across the columns, so we can actually see where the missing values are. And you can see there's 10 missing values in engine capacity, and all the others have 0. But I want to get it in a nice sort of a way we can see it. So what I'll do is I'll use this as a Boolean logical array. So I'll run that, and you can see it'll be only a true if in engine capacity, because we're checking only true if there's at least one missing value. So I can use this Boolean array as an index in data.columns. And what that will look like is will just be the columns that have missing values. And to take it one step further, I can just type values to clean up what that looks like, which will just return the actual... Did I run that properly? Okay, hold on. If I print it, it should do it. Yeah, it just shows that one little array. So columns with missing values, just engine capacity. So next thing to do is check what kind of data types are in engine capacity. Now engine capacity, and then we type .dtype, and we have a float. So that means we can fill the missing values with the mean. Very easy. We just take the mean of all the other values and then fill in the missing values with that amount. So data sub engine capacity dot fill NA. This function allows us to fill any missing values with a given value, and the value we're going to give it is just the mean of the column. and that will be the new column. And when we're done, why don't we print out the total missing values one more time, and we should have 0. Sure enough. Okay, let's move on to encoding the features. So take another look at the data. You can see we have a fair number of categorical features here. Features with text labels rather than numbers. In addition, we have a whole bunch of true-false values here, and some here as well. I notice, these features don't actually have any description. If you look at the dataset, and I check all the features here, the descriptions are all the same. Is the option like alloy, wheels, conditioner, etc. is present in the car? So we can assume that each one of these features, 0 through feature 9, tells us something about the car, but we're not really sure what. Perhaps when we check the correlations later, we can clear that up. Or at least we'll be able to see how much predictive power each one has. But the first thing I want to do is, here, I'll just make a markdown. And first thing is, let's just make all the Boolean columns into integer columns. It's very simple to do that. We're just going to say for column in data.columns. So data.columns is just a list of all the columns. So we're going column by column, and that's actually just name by name. If data.dtypes, which is a list of the dictionary of the data types, and we're going to index at column equals bool. So essentially we're saying if the column is of Boolean type, then data subcolumn equals data subcolumn dot as type numpy.int. So we're just changing the data type, and we perform this integer type conversion on the true and false, so it will just become 0 and 1, and we'll have binary columns that way. All right. So then we will take a look at the number of unique values in each categorical column. So a categorical column we can define as just any column that doesn't have a numeric value, and at this point it will be, if you look at the data.dtypes, there are these. It's called it has a type object, which is really a string. So what we'll do is say we'll get a dictionary that's going to map a column name to the length of unique values in that column. So data.column.unique, and take the length. For every column in data.columns, if data.dtypes subcolumn equals object. Right, so for every categorical column, let's get a length of the unique names, of the unique values. All right, and we notice a few things. First of all, there's one that's standing out. Model name has too many unique values, 1,118. So let's drop that feature. We could keep it, but it will slow down our model, and I doubt it's going to add too much, because the more unique values there are, the fewer examples will have values in common with each other. So for our purposes, we're going to drop it. Data equals data.drop. What's it called? Model name. And we're dropping from axis 1, column axis. And then the next thing to notice, hold on, I'm going to mark down. Transmission, this one, only has 2 unique values, so we can encode it as a binary feature. And binary features are easier to encode than nominal features, because all we have to do is set one of their values to 0 and the other to 1. So let's take a look at the unique values in transmission. And we have automatic and mechanical. So what we'll do is create a mapping, transmission mapping, that's going to map automatic to 0, and it's going to map mechanical to 1. And then it's very easy to replace. All we have to do is data sub transmission dot replace, and we can just pass in the mapping, pass in the dictionary here, and it will automatically apply the mapping to each element in transmission. Oh, I should also I have to set it as the new column. Okay. all the remaining features can be one-hot encoded. There are no ordinal features in this dataset. All of the categorical features have there's no order between the values. So we're going to one-hot encode them. So I'm going to make a function called one-hot encode, and it's going to take in a data frame, a list of columns, and a list of prefixes. And we're going to start by making a deep copy of our data frame, just so that we don't accidentally, we aren't modifying in place. It's just good practice. And then column, comma prefix. So I'm going to be iterating through the columns and prefixes that I provide, 2 at a time. So I want to zip together columns and prefixes. So zip will pair 2 lists up element-wise into tuples, so that I can iterate 2 at a time, like this. So then for each column and prefix pair, we're going to create a dummies data frame using pandas.getDummies, and we're getting dummies for df subcolumn, and we're going to apply the prefix that goes along with the column. Right. And so pandas.getDummies, let's say if we do this for engine type, that's what we're trying to predict, but I just want to use it as an example, and no prefix. It should be data. You can see each unique value in engine type has a new column now, and the original example's value has now just been encoded as a 1 in the respective column. Now if I include a prefix, how about eng? It will just show eng at the beginning of each column, so that we don't have duplicates when we encode multiple columns. Alright, so I'm going to get those dummies for a given column and prefix. Then I'm going to concatenate, using pandas.concat, the original data frame and the new dummies data frame side by side. And then we will drop the original column from which we created the dummies. That's all. We just return df after that. And we want to construct a list of columns and prefixes that we want to one-hot encode. So that's just going to be everything here except model name and transmission. Everything else we're going to one-hot encode. So I just have the list right here. I'll just paste it in so I don't have to type it out. These are all of those in this list that we didn't already deal with. Then we also want some prefixes to go along. I'm just going to use the first letter of each column because they're all unique. So it looks like this, M, C, E, B, S, D, L, and they match up one by one. So these two will get zipped together within the function, and then we can iterate through them to it. Like manufacturer name will go with M, color will go with C, and so on. Alright, so now what I'll do is data equals one-hot encode. We'll pass in data. We'll pass in columns equals one-hot columns. And prefixes equals one-hot prefixes. Alright. And after that, let's take a look at data. You'll see we have 119 columns now. We have all our original features, except we have a bunch of one-hot features all at the end. These are all just one-hot columns. And you can see the prefixes are there. So, let's check. Okay, we have this one left. Alright. So, if we were to print the remaining non-numeric columns, we can get this just by checking the data types and then creating a logical array for each column to check if each data type is object. So then we can sum across that using pandas sum function. So what this is just saying is sum up all the count of object columns in data. And we only have one, and that's because we still have this engine type to deal with. So let's go ahead and start encoding labels. And this is very simple. We'll do this a similar thing as we did earlier with the automatic and mechanical. We'll just map each value to a unique integer. So data sub engine type dot unique looks like this. We have gasoline, diesel, and electric. So we're going to create a mapping, label mapping, and we're going to have gasoline go to 0, diesel go to 1, and electric go to 2. And then all we have to do, dataset engine type dot replace label mapping, and make that the new column. Alright, now let's just copy this again, just take another look. We now have no remaining numeric columns. So now everything is in, we have no remaining non-numeric columns. So everything is in numeric form. Now seems like a good time to visualize the correlations. So if we have any features that are too highly correlated, that can actually negatively affect the performance of our model because they'll be redundant. I'm talking features with correlations of like over 0.9, like really, or negative 0.9. Really, really highly correlated features. We'll just remove one of them, keep the other one. So I'm also going to exclude the one-hot columns from this because we just have so many. We have like 119 columns now. So what I'll do, find where that starts. These are all one-hots. So right here, this is the first one-hot column. So duration listed is the last column that before the one-hots start. So I'll just slice the data frame. I'm targeting all rows, and then the columns I'm going to start from the beginning to duration listed. So the first one is transmission. I could just leave this blank as well. But this is saying, okay, only give us the slice of columns from transmission to duration listed, which means everything but the one-hots. And then target all rows. And then we're going to construct a correlation matrix from that using .core. And we'll store that in core. Alright, and then we will plot a heat map using Seaborn. Let's make a new pie plot figure with a fig size of 18 by 15. And then sns.heatmap. We'll pass in core because we're getting values from core. And then we'll turn on annotations. We'll set the vmin, which will just it will ensure that the colors of the heat map start from -1 because we always have +1 in there because the correlations are compared with themselves, and any column correlation with itself is just 100% just 1, right? 1.0. But -1 is probably not going to be present. So we just want to make sure that the color bar is scaled completely. Then CMap, I think the default is rocket anyway, but I just want to keep that on there. Just a color map to make it look nice. Okay, and let's just take a look. So here we go. We have these correlations, and we want to, first thing we're looking for is any extremely high, extremely strong correlations. So anything above like 0.85, 0.9, and anything below -0.85, -0.9. And I'm not seeing any of those. The highest I see is 0.7, and then we also have on the negative side is -0.68. But that's okay. We can keep that in. And that's also, it's interesting. Feature 0 seems to have some of the strongest negative correlations, but we don't even know what it is. And it seems to be correlated with all the other feature 1 through feature 9. So my guess is maybe feature 0 is some sort of combination of the other features 1 through 9. Interesting. Features 6 and 7 are also correlated. Okay, the next thing to look at with the correlation matrix is if your target variable is in here, you can check, are there any features that are going to be doing like all the heavy lifting. And our target variable is engine type, this one. And it looks very uncorrelated. It doesn't look like we have any really strong correlations for engine type, this one right here. It's also here. All very neutral. So that means if we do get a high accuracy, which I hinted earlier we will, it's not because any one of these is predicting for us. It's a very healthy combination of all of them is going to give us quality predictions. Okay, let's move on. We're going to split and scale the data now. So y is going to be what we're trying to predict. That'll be data sub engine type dot copy, and x is going to be everything except what we're trying to predict. So I'm dropping engine type from axis 1 and making a copy of that. Alright, now we will scale the x. So using a standard scaler from sklearn, this will give each column in x mean 0 and variance 1. And that'll allow each column, each feature, to take on a very similar value, range of values. That will help the model's performance. Alright, so x equals scalar dot fit transform x. And that's it. X now is scaled. If I want to see it as a data frame, we'll lose the column names, but that's okay. You can see each column now has values centered at 0, and most of the values lie between -1 and 1. So now let's split into train and test sets. So for this, we'll use the train test split function from sklearn, and it's going to split x and y into xtrain, xtest, ytrain, ytest. We'll specify a train size. 70% is a good number, and we'll include a random state. That's because it also shuffles the data. This really nice function will shuffle our data for us, so we don't have to do that. And the random state ensures that it's always shuffled the same way. So if we want to reproduce the results, we'll keep the same random state. Alright, and we're ready to train our model. So modeling/training. So I'm going to check the shape of our input before we start. So we have 118 features. That will be important when we create our Keras model. So we'll start with an input layer, tf.keras.input, and the shape is going to be the length of our feature vector, so 118. And then we're going to have just 2 hidden layers. That's all we really need. tf.keras.layers.dense, 64 activations, RayLow activation, very standard. Passing in inputs here, and I'm going to duplicate it and then pass in x to the second one. And then the outputs will be another dense layer with 3 activations this time, 1 for each class, which was, I believe, what was it? Electric, diesel, and gasoline. Yeah. So 1 for each of those. And we're going to have a softmax activation here. And that softmax will return 3 values between 0 and 1, where their sum adds to 1. I think their sum adds to 1. Actually, don't quote me on that. I'm not sure. But there'll be probability values for each class. So the one with the highest probability will be chosen as the classification. And we'll pass x into outputs. Then model is tf.keras.model. We'll pass in inputs and outputs, and then we'll compile it. So we'll use an atom optimizer. It's a very standard, very good optimizer. And then loss, we'll use sparse categorical cross entropy, also known as log loss for multi-class classification. Then metrics will just be accuracy. And we'll store the model's fit history in history. So I'm going to train it on xtrain, ytrain, so our train set. And then, whoops, our validation split will be 20%. So we're going to reserve 20% of the training set for validation. Our batch size, 32. Epochs. Alright, so I did 100 epochs and I wanted to use a callback. tf.keras.callbacks.early stopping, which it will automatically stop the training when the validation loss or whatever quantity you monitor stops improving, and it will restore the weights from the best epoch. However, I found that even after 100 epochs, the validation loss never went back up. I'll keep it in here just because it's nice to have in case someone wants to train it for longer. We might be able to get better results, but you'll see it's we can't get much better. All right, so val loss monitor means this is the quantity we're tracking, and we specify a patience level, which is we'll do 3. So that means after 3 epochs, if the validation loss does not improve for 3 epochs consecutively, we will stop the training and restore the weights from the best epoch. So restore best weights equals true. Alright, and then we'll run it. And as you can see, after just 1 epoch, we have 100% accuracy in the validation. So this I really attribute to how clean and beautiful the dataset is. There's a healthy number of features, and there's very few missing values. And I wouldn't expect that engine type would be 100%, that you'd be able to guess it with 100% accuracy based on all the others. But I guess the neural network doesn't lie. So yeah, this will just go. Why don't we get the results after? We'll just evaluate the model on the test set to see how it does on completely unseen data. So I'll just pause the video and start it up when this finishes. All right, it's finished. Let's take a look. And we get 100% accuracy on the training set. No surprise there. If you look at this, the progression, you'll see after a while the training loss becomes so low that it's no longer quantifiable. It just goes to 0. And the validation loss never stops decreasing. Now I assume if we trained it for longer, maybe do a few more 100 epochs, we may be able to early stop. It may start to overfit, but I mean, what's the point? We got 100%, and that's on a pretty large set of examples, right? I think y test, the length of the test set. We could do .shape. Yeah, this is on 11,000 examples. We got 100% accuracy. That's unbelievable. Alright, so that will conclude today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.